Every time a global AI system processes a prompt, translates a document, or predicts a purchase, it is executing an act of translation. It is converting abstract human concepts into continuous, highly structured spatial geometries. These spatial coordinates, known as word embeddings, are not programmed by hand. They are generated iteratively by algorithms calculating the statistical likelihood of words appearing next to each other within massive text databases like Wikipedia or Common Crawl. The mechanical rule of this architecture is straightforward. Context dictates spatial proximity. Words that frequently share the same surrounding text are mathematically pulled closer together in the high-dimensional space. But because these embeddings are trained on unfiltered human text, this exact mathematical optimization acts as a mirror. The vector space captures, distills, and mathematically solidifies the prejudices of the societies that authored that text. Geometric positioning solves semantic analogies. Subtracting man from king and adding woman lands precisely on queen. But applying this exact arithmetic to historically biased data exposes a darker alignment. Subtracting man from doctor and adding woman lands directly on nurse. Today, we examine the exact mechanics of these vector spaces and how researchers quantify this deeply rooted prejudice. We will see how engineers attempt to mathematically debias the matrices and how tech giants manipulate these architectures to operate at the scale of billions of users. To understand the scope of this phenomenon, researchers needed to transform abstract sociological prejudice into measurable distances. They initially relied on the word embedding association test, or WEAT. This test calculates the relative cosine similarity between target concepts, like male or female names, and specific attributes, like career-oriented or family-oriented words. However, traditional WEAT had a significant vulnerability. It relied on strictly predefined binary attribute groups to function, making it highly sensitive to statistical outliers and varying sample sizes. This infographic outlines how data scientists resolved those vulnerabilities by developing SD-WEAT. Utilizing standard deviation across multiple permutations, SD-WEAT measures bias across runs without predefined term groups. This testing confirms newer BERT-based architectures score lower in bias than older glove embeddings. But static embedding matrices are only one part of the pipeline. Modern large language models dynamically generate contextual representations, requiring researchers to develop the LLM relative decision test to probe their associative memory. When forced to make relative evaluations between two candidates, these dynamic models repeatedly expose hidden prejudices. In simulated trials, LLMs consistently recommended higher loan denial rates for Black and Hispanic borrowers, and disproportionately directed marginalized patients towards psychiatric screenings rather than standard medical care. These outputs are not abstract, unexplainable glitches. They are explicit statistical associations and mathematically solidified coordinates parameterized directly into the core logic of the model. Beyond sociolinguistic bias, the spatial mechanics of modern context windows create a severe, purely architectural vulnerability. Contemporary LLMs can ingest entire legal libraries or massive codebases in a single prompt, but empirical studies reveal a cognitive blind spot known as the lost-in-the-middle phenomenon. These models do not process extended data evenly. This graph tracks how a self-attention mechanism allocates focus across a context window. The U-shape illustrates heavy prioritization of data at the beginning and the end. Look at the absolute middle. The model almost entirely neglects information buried centrally, dropping to 18% retention. The consequences in high-stakes environments are immediate. If you ask a model to act as a zero-shot evaluator for a complex medical diagnosis or a legal contract, simply flipping the order of the provided options in the prompt can entirely reverse the model's decision. The model's output is frequently driven by the geometric placement of the tokens, rather than the actual semantic merit of the information. Correcting these mathematical prejudices requires engineers to intervene at 3 distinct stages of the machine learning pipeline: pre-processing, in-processing, and post-processing. Pre-processing uses targeted data pruning to surgically remove influential, biased data points before training begins. In-processing embeds fairness directly into the gradient optimization, penalizing the model during training if it generates biased representations. This illustrates geometric orthogonal projection, which mathematically alters the vector space after training. Engineers compute the geometric direction of a bias, like gender, and project neutral vectors away from that axis. This ensures doctor sits perfectly equidistant from male and female concepts. But these geometric fixes introduce a heavy engineering trade-off. Excessive manipulation of the space introduces semantic loss, starving the model of the sociolinguistic context it uses to make accurate predictions. Attempting to engineer a perfectly unbiased foundational model degrades its core predictive accuracy on standard tasks. Despite these limitations, the raw utility of vector spaces has become the technical standard for high-scale enterprise systems. The same mathematical principles used to map the English language are actively used to map human behavior and global supply chains. Spotify's BART engine treats an individual user's listening session as a sentence, and the individual songs as words. By running a skipgram algorithm over these sequences, the AI pushes tracks sharing similar contexts closer together in an 80-dimensional space, accurately clustering music regardless of manual genre tags. In the global e-commerce sector, the challenge is sheer scale. Alibaba manages billions of distinct commodities. Traditional collaborative filtering algorithms fail under the weight of datasets this sparse, because an individual user only ever clicks a microscopic fraction of the available catalog. This architecture details Alibaba's e-guess model. It turns user-product interactions into a massive directed graph. To place brand new items lacking click data into the vector space, the algorithm dynamically aggregates side information, weighting the base item identity against supplementary data like shop identity. By abandoning literal keyword matching and treating historical user behavior as a traversable geometric topology, tech giants can filter billions of data points to generate highly relevant predictions in milliseconds. We arrive at a central tension. Creating an unbiased, lossless foundational model is a mathematical impossibility. Fairness is not a static mathematical absolute. It is a complex, evolving social construct. Recognizing this, the global regulatory environment in 2025 has moved away from regulating static models, focusing instead on how they are used. This diagram outlines the new legal mandate. Liability has pivoted away from base models, moving directly to enterprise deployment. Companies are now required to implement Phase 4 continuous monitoring, deploying automated drift detection to track AI performance as real-world data changes. What began as a method to represent words numerically has transformed language from a set of discrete symbols into a continuous, interconnected space. This mathematical architecture allows models to navigate complex contextual relationships that were once thought to be the sole domain of human reasoning. This is how intelligence emerges from data. Whether predicting customer lifetime value, scaling global search, or unmasking historical prejudices, the rule remains the same. Language and intent must first be mapped before they can ever be understood.